All right, are we ready to begin? Yeah, cool. Welcome to the Canadian Bioinformatics Workshops. If it's your first time taking a workshop, it's great because this is my first time instructing a workshop here, but I did take workshops with the Canadian Bioinformatics app. I also watched a lot of their tutorials when we'll talk about my postdoc. When I did my postdoc, I relied heavily on their, here's how you analyze flow cytometry data with R. That was pretty cool. It was probably the best workshop I've ever watched. Okay, so I guess this is terms and conditions. And we're gonna start module 3. So module 3, we'll talk about what these things are, conditional statements, loops, and functions. All sound scary, but I'm gonna make them really, really friendly and nice. You guys already saw that. Don't worry, we'll get a chance to do that again when we'll do a practice exercise to kind of reiterate what you've done yesterday. So again, I wanna welcome you and I wanna introduce myself. My name is Ido. I did my PhD at the University of Alberta. That's why Robin and I were talking about Edmonton so much. My specialization is environmental microbiology, specifically polar and alpine. Did a little bit of oil sands reclamation because Alberta. Pretty much self-taught bioinformatician. Because necessity is the mother of invention. So I've been around the block. I don't know how many of you have ever got a chance to use any high throughput sequencing platforms, but I pretty much used all of them. So I was there from when pyrosequencing was around to when Illumina and Ion Torrent came in, and also worked on Oxford Nanopore pretty early on. When Illumina started coming out with their second set of chemistry, which dished out a lot of data, but was relatively noisy, and Ion Torrent came in with their first set of chemistry, which was even more noisy, all of the software that I had to use crashed. And that was the key for me to be how do I reverse engineer what my software is doing so that I can finish my PhD? And that's how I taught myself coding, and what R was a basic part of it, because it seemed that all of the analysis was done in R. So I was like, okay, how do I get the data structure that I need to plug things into R and do stuff on my own? And so the data that I was using was specifically metagenomics, but also a little bit of multi-omics, plugging in a little bit of metabolomics and stuff like that. So that's where I did my PhD, did my postdoctoral studies at UBC, the Department of Chemical and Biological Engineering, where I worked a lot of building computational pipelines, specifically geared towards identifying key microbes in water treatment facilities. So who's doing most of the work, who might do damage by clogging the wastewater treatment facility and so forth and so on. What's their metabolic capability? Can we use some machine learning tools to find some indicator species for when things go wrong? I also worked on some disturbed sites. I don't know how many of you have been living in BC for a long enough time, but in 2014, we had a pretty major tailings pond breach in Mount Poly mines, and then millions of tons of waste from mining and wastewater basically got dumped into a pristine lake. And I was working on trying to assess how far down all that waste kind of distributed, and then try and figure out if we can use all these molecular ecology techniques and machine learning tools to try and figure out if we can identify disturbed sites versus non-disturbed sites. So lots of stuff. I have been teaching at Langara College for about 6 years. Was at the ground floor here when we started building our bioinformatics bachelor's program, developed multiple courses for that program. And I'm really excited to share my experience with you. So what will this module cover? We will talk about conditional statements, basically talk about if something happens, do this. If not, do something else. We'll talk about loops and how we control flow inside loops when we need to do things over and over and over and over and over and over again. We'll talk about how to write our own functions. I don't know if you guys realized it, but you guys have been using functions all throughout yesterday. When you use, let's say, ggplot, that's a function. Okay, so we're going to learn how to write our own functions. And throughout this, we'll constantly try and focus on good code practices. Now, if you find it kind of like, oh, it's hard for me to remember, it's okay. I can't pretend that when I code, it's perfect in terms of the way it looks, right? You always worry about if it's working, and you then make sure that the prettiness comes later on. Okay, so the goal is to get things to work. So learning objectives for this is you will be able to use some conditional statements to control code flow. For example, if else, and case when. We will learn how to write, and you will be able to write loops to handle repetitive tasks, and we will learn how to use next and break to control the flow within loops. We'll understand the principles of generalized and reusable code and apply good coding practices throughout these. And then we'll see maybe one of the best examples for generalized reusable codes, which is how we write our own functions in R. But before we begin, let's switch to our manual and do our warm-up exercise to make sure that we have the R juices flowing again, so you get to hopefully repeat what you've done yesterday. So yeah. All right. So we've survived our warm-up. Hopefully everybody now kind of like got the feel for what it's like to code in R again. And can start with our first point of confusion, which would be, or second point of confusion now, which would be conditional statements. So for those, before we begin, we can start highlighting our coding principle, because our journey to good coding principle begins here. One of them you guys already experienced, right? Piping is great one, because you don't have to specify your data all the time in every function. You can just pipe it, okay? But we'll talk about those, okay? So the first things first, whenever possible, we are going to avoid hard coding. What is hard coding? You notice that for every function, you have to put in arguments, right? And you had to specify the arguments. Some cases, we had to specify the exact argument, which would be, for example, I want you to download this file, okay? If I just want you to download this file, then I have no option. I have to hard specify it. But sometimes I want to say download the first file, and the name of the first file might change. So I can't hard code download, let's say, Yasmin's file.csv, because now it's the first file. What if it becomes David's file.csv? Now is the first file, okay? And I always want to do the first file. So I need to be able to specify how to specify the first file without hard coding, right? We need to make sure that in some cases we'll have to put arguments in a way that is flexible, such that our code doesn't break if one of the conditions change, that we have a contingency. That's what hard coding means. We'll talk about it. We'll give examples for that. The second one, which you already got to experience, is don't repeat yourself, right? Don't repeat yourself. That's a very inefficient way of coding. So, and a great example of that is when you're doing ggplot, you put your table inside ggplot, or you piped the table. In that case, whatever you put inside ggplot, you don't have to reuse. So Yasmin had this great question. She was like, why do I have to put these here and not in the geom, for example? If you specify stuff in ggplot, ggplot will know to use that stuff in all subsequent geoms. So imagine that you want to do, within the same graph, you want to do a histogram and you want to do a line plot, and you want to do a bubble plot or a dot plot, okay? If you won't specify the data as a pipe or inside ggplot, you will have to specify it for every one of these geoms. If you don't specify the X and Y in the AES inside ggplot, you will have to specify it for every geom, right? Same for the color and the fill and the shape. So we don't want to repeat ourselves, so we're going to put everything inside the ggplot, right? And we'll only change it wherever we want things to be different. So for example, if I want my scatter plot to use different data, that's where I'll insert the different data. But everything else goes to where we don't have to repeat ourselves. Another great, we'll talk about that later in this module, is write-focused functions, okay? You saw now that you have a workflow, right? We loaded the file, we loaded our data, we processed our data, and we plotted our data, okay? Let's say that we want to share this with our buddies, right? We can send them our script, and then they look at the script and they were like, well, what did they do here? And why did they do it there? And why did they put the data here? And I don't understand it. And my coding style is so different than their coding style. We can wrap the script that you guys just wrote, we can wrap it in a function that will allow them to write it in one single line. We'll call it run pipeline, okay? And run pipeline will just take a link to a file and we'll do everything and we'll output a plot, right? So when we're doing something like that, that's called writing a focused function. We'll talk about actually if that's a focused function or not later on, but it makes your code much more readable. Instead of having a gazillion lines, we have only a single line. Just like instead of like having read CSV, for example, when you used it, had inside of it, under the hood, it runs a lot of lines of code that you guys don't see and you don't need to run and you don't need to read. Because if you had, it would be really confusing. Instead, you can just run read CSV, my file. Does that make sense to you guys? So that's why functions are really important and really important for like good coding practices. We don't have to write a million lines of code. We can just substitute them for one line of code. Okay, that makes code much more readable. When you design your function, use default arguments. Why do we want to use default arguments? I want to throw like a definition onto you right now. When you guys write functions, you are choice architects. You design what choices people use, right? Just like when we designed this door, the choice of what handle to use to make sure people know to push it and not to pull it, that's a choice architecture, okay? You noticed for read CSV, the only thing you specified was the file name. But there were a lot of other arguments out there to help run that function. For example, is there a header? Is there a row name, right? So all these arguments have default values. And as you noticed, none of us changed those default values because we are all lazy. That's what we are. Like when we use stuff, we just want to use it, right? We don't want to spend time thinking about, oh, what do I have to do here and what do I have to do there? I just want things to run, right? And so when we'll talk about writing as good code practices, when we'll write functions, we'll try and put the arguments that would serve the people who use that function the best so they don't have to think about it, okay? We also want to document our code, right? So for example, you have all these solutions to my questions, right? You can add comments next to them. Here is what I've done here, and here is what I've done there, and here is why I use this argument, right? And here is what this argument does. You can add comments, and when you add comments, when you go back to your code in 6 months from now, you'll be like, oh, that's what I did it. Thanks past me for writing it, okay? So documenting your code, and this one, I won't explain now because it's a little bit hard, it's a harder philosophical concept, but R runs multiple environments. When you want to be aware of which environment you're found in so that they don't clash and you get error messages. We'll talk about it when we'll write functions. Okay, so those are the coding practices that we will practice. Okay, when we run code, when we write code, sometimes we want our code to run only if a condition is met. Does that make sense to you guys? For example, Yasmin works with, is going to work with RNA-seq. Okay, maybe, I don't know if you guys know what RNA-seq is, basically sequencing RNA molecules. Generally, you want to do it when you want to test for which genes get expressed at what level. Call this differential gene expression. What if Yasmin wants to run a code only if the gene expression values are above a certain threshold? And she doesn't want it to run on stuff that is low expression, only on higher expression, right? We need to make sure that R understands us. We need to make sure that R knows when to run a code only when a condition is met. And this is where the if statement comes into play. If statements, what they do is that they test if a condition is met. When we say a condition is met in computer language, we have to transition to logic, okay? When a condition is met, we call it the test is true, okay? So we test if the answer is true, okay? And if the answer is true, it will run the code. But if the answer is false, which is the opposite of true, it will not run the code. So far, you guys good with me? Okay, so here is how it is. Here is our condition, the test. We're testing. Answer is true, running the code. Answer is false, going around the code, not running it, running something else, running the rest. Does that make sense? Or maybe running nothing. Does that make sense to you guys? Any questions about this? No. Okay. Here is where things get an example, not interesting. Okay, I was gonna say here's where things get exciting, or more exciting even, but no, now it's just an example. So here's our chunk of code. It's called code. Okay, that's our chunk, code. Running, reaching our test. For example, we want to test if it's raining in Vancouver, right? And if it's raining in Vancouver, we're test, it's raining in Vancouver, looking outside, equals true, right? We're like, wow, it's the first time ever it rained in Vancouver. Okay, what a surprise. Okay, it will print that, and then it will continue running the rest of the code. Okay, does that make sense to you guys? So for example, if we're looking, again, thinking about Yasmin, right? Yasmin runs her code, processing her data, processing. Now we come to the moment of truth. We want to test if our data contains highly expressed genes. So it would be like, if gene expression value equals or larger than something else, than our threshold, if that equals true, run this analysis on it. Okay, does that make sense to you guys? Okay, run this analysis. So it'll be like running the analysis for highly expressed genes. Bam, 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 bam. Finished. Now I'm going to run the rest of my code. Okay. So again, the if statement will only be executed if raining equals true, or if high expression equals true. Okay. If that is equals false, it will just run the rest of the code without running this.
So this means no genes are highly expressed?
No genes are highly expressed. Okay? But that's a great question, because what if no genes are highly expressed? Would I want to know that? I probably want to know that, right? And so that's where else comes in. Okay? So we have if, else. Okay? So what is an else statement? Else statement is the alternative. What happens when my test is false? Okay? So the idea here, what am I doing when the condition isn't met? Okay? So let's look at our scheme here. Running our code, we got to our test. Let's say again, raining in Vancouver. If it's raining in Vancouver, printing, what a surprise, and then continuing with the rest of our code. Okay, what a surprise. If it's not raining in Vancouver, that's false, right? Raining in Vancouver equals false. What am I doing? I'm printing. Are you sure it's not raining in Vancouver? Okay, that would be, and then I'm going to continue running the rest of my code. So if we're bringing it to Yasmin's example, again, we're running our data, processing, right? Processing the tables, making sure we have good quality data, whatever. Now we come to the moment of truth. Do we have a highly expressed genes, right? Gene expression value larger than something. Does it equal true? Equal true. If it equals true, we're running our differential gene, highly expressed genes, blah, 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 and then continuing with the rest, okay? If it equals false, what did we say what's the case here? We don't have any highly expressed genes, and we would like to know that. So if it's false, the else could be print did not find any highly expressed genes. Continuing with the rest of my data. Does that make sense to you guys? So for David, it could be did not find any frog, whatever frog, sorry, I forgot the name of the frog, but whatever, which one? Coastal-tailed frogs, I'll remember it from now on, okay? Did not find any coastal-tailed frogs in... Okay, all right, tailed frogs in the data, okay, in my eDNA data. Or it could be found out of, let's say, 60 sequences, 30 were classified as tailed frogs. Yeah, that's for example, how we would use if and else. All right, cool. Here are where things get even more interesting. If and else statements work for scalar values. How many of you heard the word scalar before? Nobody, right? Man, this gives me flashbacks to like high school math. It's not, and physics, not great memories, I have to say. Okay, but the point is that scalars are just individual values. Okay, a single element, let's say a single element in a vector. Okay, so you guys remember, for example, you had allele values. Okay, so allele values, we can just use one, right? So for example, if allele value equals 18, okay, and it only works on, and so that's basically what it is. But what if we need to work on a vector of values? Okay, what if we need to work on a vectorized, right? And so if else basically can only work like that, right? If like my argument can be singular value, do something else, singular value, do something else. Okay, if I want to work on vectors, if I want to run an if-else statement that is designed for vectors, which you guys have already used yesterday, right? Remember, like basically lists of values. There is a vectorized version for it. It's called if-else, and it works the exact same way, only instead of writing if separately and else separately, you write them as one function and it saves you time. If else something equals something, do something to this vector, otherwise do something else to this vector. That's it, we'll practice all of them. And sometimes we want to do multiple comparisons. So for example, what if when Yasmin analyzes her data, she wants things that are super highly expressed and things that are moderately expressed and things that are really underregulated and things that are even more underregulated. And she wants for the super highly expressed to do something, and for the moderately highly expressed to do something else, and for the seriously underregulated to do this thing, and for everything else, do nothing. Okay, we want to be able to run multiple conditions. There are ways to do it. For example, we can chain a gazillion if-else statement. If expression equals x, do this. Else, if expression is slightly higher than x, do that. Else, if x is lower than this, do that. Else, do something else. Okay? we can do that. Or we can use a really nice function from the tidyverse that's called case when. And there you can be like, for this, I want you to do that. And for this, I want you to do that. And for this, I want you to do that. And then for everything else, do this. Okay? Like really, really structured, really, really nice. Okay? So as we'll see, it will save us a lot of time. So for good coding practices, it will save us on a lot of like repeating ourselves. Okay? So any questions about why we would want to use conditional statements? Any question about the philosophy behind conditional statements? Questions? No. Okay. So now let's move to do some examples. I think I have a lot of examples there, so we don't have to do everything. Let's just focus on like getting at least one of each. And if we can do the rest, that will be bonus. In any case, a solution key will be posted to the course website so you can play with it. Okay. So loops and how we control flow within loops. Why would we want to use loops? We want to do the same thing over and over. Good. I always have to make sure people get the joke. So okay. We're going to start this with an honorable mention. R has a lot of different types of loops. We're only going to focus on one, that's the for loop. But the one thing that we want to honorably mention is the while loop. Okay? What is the while loop? A while loop runs a chunk of code over and over and over and over and over and over while a test is true, right? Just like if statement says, if a test is true, run thing, while says, if a test is true, run thing over and over and over until it's not true. So for example, let's just say while x is larger than 8, or while x is smaller than 8, runs something, okay? Run my code over and over and over and over. And I can have a count variable, and I will say x equals 1, okay? And while x is smaller than 8, run my code. So I'll have code x plus 1. Now x equals 2. Run my code, x plus 1. Now it's 3, all the way until it's 8, and then it will terminate, self-terminate. Does it make sense to you guys? So that's what's going on here. We have a logical condition, while x equals 8, right? If it's true, we're running our code, checking our condition again, running our code. The reason why we won't do this is prone to endless loop. For example, you can say while x is smaller than 8, and you will forget to add 1 to 8 every time you run your code. And what will happen is that your code will run forever because you forgot to set the condition to actually break the while loop, okay? And so that's something that we don't want to do. We want to avoid. We don't have to use it. We want to be familiarized with it. We want to run a loop that actually knows when to stop itself, a self-aware loop, if you will, okay? So for loop, we'll talk about it in the next slide. We can think about it as a self-aware while loop. So what is a for loop? A for loop runs a code of block for every element in a vector, okay? So we can think about it as a loop that runs a block of code while there are still elements in our vector to iterate over, okay? So think about all the, let's say the quality control vector that we had, right? The quality score vector that we had. We can say, for every element in this vector, run this very complicated line of code. It's no longer if print something. For every one of these, run a complicated line of code. It could be, let's say, a list of FASTQ file names. Those are the files that you would get from high throughput sequencing. And it would say, for every file on this list, run this code that processes the file and removes all the poor quality sequences out of it and save only the good ones. Okay, and it will go file number 1, bam, 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 bam. File number 2, bam, 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 all the way to last file. And what would happen after the last file? Will we have any elements in our list of file names? Will we have any elements in our list of file names once we hit the last one? Will we? No, right? So it will know how to stop, okay? So for every file in our file list, run this. Once I hit the last one, there is nothing next after it, I know how to stop. Okay, does that make sense to you guys? If not, we'll, okay? So we have a vector, right? We're like, here is our sequence of items, okay? Item number 1, execute the code. Did I reach the last item? No, execute the code. Did I reach the last item? No, execute the code. So I'm progressing from item number 1 until the last item. Reach the last item, good. I'm going to run it one last time for the last item, and then I'm going to break the loop. Okay, does that make sense to you guys? So again, we can think about it as a special case of a while loop. While I still have items in my sequence to do something, I will do it, and if I don't, I will break. And that way, I don't have to manually make sure that I set something to break my loop. The loop knows when to break itself. Yeah.
The graphic looks like it shouldn't be last item reached, yes, exit loop, last item reached, no, execute statements.
No, it's like last item reached. Yeah, it should be flipped. Should be flipped. Yeah. Last item reached. No, execute statement. Yeah. So good lesson to when you rip off figures, make sure you rip them off from reputable sources. So you're right. That's a great catch. That's a great catch. So you guys got the concept. Okay. So here is how it would work. Okay. For every unit in vector X, let's say every file in my file list, do something. When I'm done, when there are nothing left to do, exit the code, exit the loop. Okay. So within a loop, sometimes we might want to be able to skip things. Okay. And sometimes we might want to break things. Sometimes we want to break the loop independently. Okay. So for example, I can write a for loop and I would be like, I have some stuff that isn't interesting to me, so I am going to skip it. I'm going to use an if statement to skip it. Okay. For example, let's say I have a list of files of sequencing. Some of them come from, let's say, ponds where I'm expected to find tailed frogs, and some where I don't. Okay, and so I can say, and some comes from, let's say, the desert. So I can say, if the file name contains pond, do something. Okay, do my chunk of code. Else, next, which means skip to the next file. Okay, does that make sense to you guys? Okay. I can also break a code. So for example, I can say, hey, I ran through enough files. Let's say I found 5 files from pond samples. That's enough for me. I'm going to break my loop. Okay, so I can say if number of files equals 5, break. Else, continue running the code. Okay, does that make sense to you guys? The last thing we'll cover, and we'll do it really briefly before we start linear models, are functions. You all already used functions. Every time you called if, that's a function. Every time you called read CSV or break, or what else have we used? AES, what else have we used? ggplot, geom, all of these, they are all functions. R can be thought of as a functional programming language. It works really well when you write functions and run your code through functions. Everything is a function, okay? So what are functions? Here's it's another joke. Okay, functions are reusable chunks of code, right? They help us not repeat ourselves. their structure is very, from a philosophical perspective, structure is very simple. They take input. That input is called arguments. Can you think of arguments that you've used in samples, in functions? What arguments have you used? For example, for read CSV, what argument did we use for read CSV? The file name. Exactly, right? The file name was that. For ggplot, what were the arguments? The X and Y, the data, those were our arguments, right? So it takes those arguments and it performs some operations and or computations on those arguments, and then it returns the results, which we refer to as the output. Okay, so for example, the print function, what does it take? It takes something to print as an argument. It does something to it, which is like, oh, this is what I need to print. And then it returns the result. What is the result? The print. Whatever it is, it printed, okay? That would be the output, okay? So here's the structure of functions, right? Like biologists, we like correlating structure with function. Here's what we're doing. So functions, as I mentioned, have a simple structure. Function, opening brackets, given the list of arguments. For example, file name, columns to use, whatever, okay? Whatever you want to do, you have a list of arguments. You open curly brackets, your code chunk. Once you're done, you're going to have a return statement if you need a specific value to be added. If not, the function will just return the last thing it saw. Okay? So does this make sense to you guys? Yeah? All right. We have an argument, taking the argument, doing something on the argument, and having a return statement to return what we need to return. Okay, does that make sense? Okay. So now let's move to the manual and see some examples. We won't do the summary exercise because it's very extensive. It will be good for you guys to do it on your own time. I will give, again, the answer key will be there so you can practice.